Standard enterprise architecture relies on stateless request-response APIs, but industrial operational technology operates on a continuous, uninterrupted stream of physical events. If the network drops, the factory doesn't stop. That is why PLC Edge Analytics is built as a deeply stateful, long-running C# console application. It is not a web application waiting for a request. It is the analytical engine itself. Look at the left side of this flow. A stateless REST API chokes under the latency of high-frequency 10 Hz telemetry streams. On the right, our stateful loop ingests a continuous river of telemetry blocks directly into memory without network overhead. This architecture defines our deployment model. We deploy one worker process per customer site or plant boundary. That single instance comfortably handles 30 to 60 distinct assets, rather than requiring an isolated worker for every single motor. Predictive edge analytics requires continuous data memory. By abandoning stateless web design, we guarantee that the telemetry stream is processed without interruption, exactly where the data is generated. To keep that stateful worker alive in hostile environments, we enforce strict clean architecture. The domain model operates with absolutely zero database, framework, or user interface dependencies. We explicitly removed off-the-shelf mediator libraries. We execute a custom CQRS architecture to enforce tighter generic boundaries between commands, queries, and events. We apply functional programming discipline using the LanguageDat library. When a sensor fails, the error is encapsulated into an either struct. This eliminates implicit, exception-driven control flows that crash background processes. When a specific capability is unavailable, the system defaults to a safe state using the null object pattern. For example, our PLC write-back system uses a null PLC writer. It processes the analytical command cleanly without ever sending a live electrical signal to the machinery until explicit plant approval is granted. These rigid functional boundaries ensure that unexpected data states route to safe fallback paths. The runtime survives data corruption natively without requiring a container restart. The analytical core of the platform is the continuous inference loop service. It groups the infinite telemetry stream into 2-minute rolling windows, stepping forward every 10 seconds. A historian polling adapter tracks per tag watermarks. It fetches the latest sensor readings from active subscriptions every second and pulls them directly into the in-process stream. Before any complex math occurs, deterministic data quality guards validate the window. They actively block not-a-number values, stuck sensor readings, and out-of-range hardware errors from poisoning the analysis. This diagram shows the digital signal processing layer. A raw time domain waveform transforms into a frequency spectrum using fast Fourier transforms. Through motor current signature analysis, the system isolates frequency bands to track broken rotor bars. We also layer additive spectral kurtosis onto the spectrum, isolating sharp mechanical shocks from the motor's standard background noise. The machine learning models require clean, physically meaningful features. We use deterministic mathematics to isolate mechanical reality first, actively preventing the algorithms from reacting to raw noise. No single statistical model can detect the entire range of mechanical and electrical failure modes within an industrial pump train. We deploy a robust 7-strategy ML.NET ensemble. Algorithms like operating cluster segmentation and neural networks process the exact same feature window in parallel, creating a cross-verified health assessment. To analyze the entire dataset simultaneously, we apply multivariate statistical process control. This diagram shows a 15-feature matrix entering a principal component analysis algorithm, splitting into Hotelling's t-squared and q-residual statistics. A data point appears safe on its own axis, but in this multi-dimensional plane, the relationship breaks, crossing the red alarm boundary. To compute this math within the 10-second window constraint, the pipeline uses the OpenVINO execution provider. This targets local GPU hardware for Onyx model inference, guaranteeing a CPU fallback if the hardware is fully utilized. By fusing these distinct statistical viewpoints, the system produces a dense anomaly score that requires a legitimate, correlated structural breakdown to trigger. High anomaly scores do not instantly notify operators. The platform is engineered to actively suppress false positives and reject weak analytical signals. Every anomaly must survive a strict validation chain. It must cross the threshold score. Confidence must exceed 90%. It must persist across sequential windows, eliminating transient spikes. The final physics gate vetoes anomalies violating mechanical reality. The evaluation then scales plant-wide using a Fiedler eigenvalue monitor. If adjacent machines decouple, the lines connecting them thin out and break, detecting systemic failure before local thresholds trip. Forcing statistical models to survive electromechanical and topological constraints filters out the noise. What survives is a verified, actionable mechanical fault. Verified faults are passed to a survival analysis engine. We apply a Weibull distribution to calculate the mathematical curve of the degradation, estimating the remaining useful life of the asset in days. The entire analytical conclusion, the anomaly score, the remaining useful life, and the JSON evidence chain is committed atomically to a local SQL Server 2025 relational database. We enforce a transactional outbox pattern during this database write. The domain state and operational broadcast event are saved in the exact same transaction, ensuring the message is permanently recorded before hitting the RabbitMQ bus. For high-velocity state tracking that does not require relational storage, the system utilizes Redis. This handles the live anomaly stream publication and distributed caching, keeping the SQL engine focused on authoritative records. Tying the operational message directly to the database commit guarantees the factory floor is notified. Even if the local network drops up the mullen of detection, the alert broadcasts the instant connectivity is restored. With the alert securely persisted, the system begins post-alert interpretation using the Ops Narrator agent, a localized large language model path. We do not use a single unpredictable prompt. This flowchart illustrates our C# enforced 4-agent pipeline. The data moves strictly from triage to diagnostic to context and finally to the narrator. Between every step, rule-based guardrails scan the text to strip out hallucinations or fabricated probabilities. Inside the context node, the system leverages entity-aware retrieval-augmented generation. Utilizing SQL Server's vector capabilities, it structurally maps the failure by matching an active anomaly code directly to the exact procedural paragraph in the manufacturer's manual. To maintain accuracy over long life cycles, the pipeline applies temporal provenance trust decay. If an operator approved a machine constant 18 months ago, the system mathematically downgrades the weight of that human input in the current evidence calculation. By trapping the language model within a hard-coded sequence and verifying every retrieval step, the system converts abstract statistical probabilities into a legally defensible, citable maintenance directive. The operator interacts with this truth through an embedded Blazor UI and Signal RHub. These surfaces are strictly operational lenses, observing the background worker process. They hold no authoritative state themselves. Even AI model updates are physically constrained. The local model version watcher uses a human-gated file lock process to stage new language models. An operator must manually review and activate the file swap, preventing autonomous, untested logic from entering the production floor. The entire runtime is monitored by an observability stack. OpenTelemetry and Prometheus track the microsecond latency of the inference loop, while Grafana visualizes the analytical health of the worker itself. True industrial analytics requires stateful processing, strict functional boundaries, and deterministic electromechanical gates. When we bound our algorithms within the hard limits of physical reality, we produce intelligence the plant floor can actually trust.